Hi, welcome to a lecture on multi-beam concepts. To begin, let's recall the concept of pattern multiplication. And that's the idea that the pattern, which is generated by an array, we'll call that F, is a product of two things. The element pattern, presuming those elements all have the same pattern, and the array factor, which is a description of the contribution of the element positions, that is the array geometry on the overall pattern. Now, pattern multiplication isn't universally applicable as a concept, but often it is, and it certainly is if the element patterns are all the same, so they can be factored out, leaving the array factor. So a broad class of problems can be described in terms of this pattern multiplication concept. We can visualize this as shown in the diagram. This square thing is meant to represent an array. That could be a two-dimensional rectangular array, but what I'm about to talk about is not limited to that particular concept. And this orange outline is meant to represent the element pattern. That's the pattern of any one element. So when you multiply that by the array factor, you can get these various beams. Right? So the red beam here is the product of the element pattern and the array factor, where the array factor is computed for some particular beam pointing. And then, of course, we can do the array factor for other beam pointings, resulting in other beams, such as this beam here and this other beam here. So the top-level idea here is that when pattern multiplication applies, we have beams which effectively sample the entire space which is available within the broader pattern of the element. Now, in many applications, it's desired to form many beams at once. So quite often, you desire not just the single beam, but you desire all the beams that would fully sample the element pattern. You might want all of these beams all at once in some applications, and not just a few of them. One example would be radar. For example, in search mode, if you're looking for a target, you might want to generate many or all beams all at once so that you can most quickly find that target. Or you might simply be tracking multiple targets, so you want to put a beam on each of the targets that you are currently tracking. In the communications realm, especially in 5G and millimeter wave applications, multibeaming has all kinds of applications, from a multi-user perspective, from a multiple access perspective, and especially in terms of beam alignment. In terrestrial 5G millimeter wave systems, beam alignment is an enormous headache, and it goes a lot faster if you can form a lot of beams at once so that you can most quickly get to the beam that's closest to the distant user that you're trying to communicate with. And of course, imaging. If you're interested in imaging a scene, you want to form all the beams so you can form the image. And this appears in many applications. Okay, so now that I've motivated the idea of multi-beam synthesis, the question is how to address this problem. How do we figure out what the right number of beams is and which beams to choose in order to fully sample the element pattern? Well, to do that, first consider the more basic question. The more basic question is how many beams are required to cover the full 4 pi steradians that's reachable by the array factor. So let's simplify the problem and not ask how many it takes to cover the element pattern, but rather how many would it take to cover all 4 pi steradians, because then we would know that the beams that are required to cover the element pattern would be a subset of those beams. And the question of how to do this for the array factor is actually a simpler problem for which the solution is pretty simple and in fact will be addressed here. So the answer is that we're looking for a basis set of beams. Now what we mean by a basis set is any set of beams. There can be multiple basis sets, but we're looking for any one set of beams consisting of the minimum number of beams from which the output of any other beam can be obtained by a linear combination of the outputs. So the idea is identify a minimum number of beams which through linear combination can give you any other beam that could be generated via the array factor. So now let's try to put this in a rigorous mathematical context. We'll start off with this expression. The beam output that is the output of beam M, subscript M enumerating the beams, is, as usual, the sum of the product of the output of elements, so x sub n is the output of the nth element, times this factor. Now remember, we're talking about the array factor here, so the coefficient of this factor is 1 because we're considering only the array geometry and not the element patterns. Right, so we have to count only for the element positions. So to do that, we have this complex exponential here, in which appears a phase propagation constant. The position of element n, p sub n, is a vector which points to the position of element n. R hat sub m is the pointing direction for the mth beam. We take the dot product of those, and that gives us the phase associated with that element of the array. And of course, there are capital N elements in the array. So let's make a definition to facilitate this analysis. We'll say that B sub n, which is a function of the beam pointing direction, is this complex exponential, which appears in this expression, but with a sign change. Now, this sign change business is done differently by every author that discusses this thing. In my particular set of conventions, I choose this particular sign change. In other conventions, you will not see that sign change, and that ripples through in ways I'll try to identify. But just note that there's no actual change in the theory here. It's just different people use different choices for signs at this step, and then that ripples through the analysis. In any event, if I now make this definition, I can then define a vector of these coefficients, the vector b, which is simply these coefficients all stacked up as an n by 1 array, going from 0 to n minus 1. And similarly, and we've done this before, we'll define a snapshot. The snapshot is the samples from each one of the n elements as an n by 1 vector. So now we can define the output of the mth beam as a vector product between the Hermitian of the beam coefficients vector and the snapshot. And because of the particular choice of sign I've made here, I have to make this the Hermitian to get the conjugate value. So this is an n by 1 array. This is a 1 by n array because the Hermitian transposes the vector and conjugates each one of the elements. And by doing that, I then get back to this expression here. So the purpose of doing all this is simply to come up with a compact expression in vector matrix form. So this framework, I can refer to this vector B as a beam. So let's explore this idea a little bit. If I have one beam, we'll call it beam m equals 1, it might have a pattern as shown here. And m equals 2 may be a beam which points in this direction. And from that, I could generate a third beam, I'll just call that y, as a linear combination of those two beam outputs. So I could take beam 1, the output, beam 2's output, multiply them by appropriate coefficients, and get the output that I would have gotten from some other beam. This is what I mean by a linear combination of beam outputs. And the idea is, if I choose the correct set of beams, then I should be able to, by linear combination of those beams, get any other beam, at least the output of any other beam. So the set of beams that does this is known as a basis set, and we can write down that basis set as the set of beam vectors, B for r hat sub naught, B for r hat sub 1, through B for r hat sub m minus 1. That is, the m beams that form the basis set. Now from basic linear algebra, we know two things about a basis set. We know, first of all, that the number of beams is going to be equal to the number of elements. Secondly, we know that the dot product between any two beam vectors is 0 as long as we're not talking about the same beam. And we refer to that property of a basis set as orthogonality. Next, it's convenient to define some additional notation. Right? So we already have this idea that any given beam output is the product of the beam vector Hermitian times the snapshot vector. So for beam 0, the subscript m here is 0 for y and 0 for r hat. And we can keep doing that for the n beams in the basis set. So if we have a basis set of beams, we also have a set of n outputs that go from y sub naught to y sub n minus 1, each pertaining to an operation on the same snapshot vector, but with different beams, namely the beams in the basis set. So I can describe this whole operation at once as a matrix operation, namely that the snapshot vector is left multiplied by a matrix comprised of these beam-forming vectors, and that gives me the set of beam outputs. And this is multibeaming. Right? Multibeaming is taking a snapshot, running it through a beamformer matrix, and getting outputs. And if that beamformer matrix is comprised of a basis set of beams, then that set of beam outputs, in fact, is everything we need to form the output of any other beam, even though we haven't computed it as part of the original beamforming operation. So at this point, it's worth noting the computational burden of this multi-beaming operation. In other words, if we use this matrix formulation to determine beam outputs, then the question is, how much effort does it take to compute? And that's most commonly done in terms of the number of multiplies. So to compute one beam output, it should be clear that you have to do n multiplies. Now these are complex multiplies, but we're not making any distinction between complex and real multiplies here, but n multiplication operations. To compute all n beam outputs in a basis set, such as what's described in the matrix equation above, well, we have to repeat that operation n times, so that's n squared multiplies. In other words, if we take an n by 1 vector and we multiply it by an n by n matrix, we end up doing n squared multiplies. Now, some of you may realize that this may not always be the case, and for that, I would ask to hold that thought and stay tuned, because we'll certainly circle back to the question of whether it really requires n squared or whether we can do it with fewer multiplies. Regardless, to compute any other possible beam output, given the output of the n basis beams, then we only have to perform n additional multiplies, because that's what the linear combination of beam outputs entails. That's a quick summary of the computational burden of this whole effort. Now, an important category of these basis matrix beamforming schemes where we can express the multibeaming as a matrix, and that matrix consists of basis beams, is based on the discrete Fourier transform, or the DFT. Now, the DFT multibeaming scheme is most easily explained by example, so that's what I'm going to do next. First, recall that the elements in any one beam vector has the following form, and I can also now add that the beam pointing direction, r hat sub m, can be written out as this expression, which we've probably used before, right? All I'm doing here is expressing that vector in Cartesian coordinates, where now the beam pointing direction is theta sub m and phi sub m. So this is just an expression in Cartesian form. We'll consider a simple uniform linear array, and this particular array has elements aligned along the y-axis. They're enumerated from 0 to n minus 1, capital N minus 1. And the spacing is d, little d. So now I can compute this dot product between the element positions and the beam pointing directions, and I find that I get n times d times sine theta m times sine phi sub m. And what I'm going to do next, because this is an example and I want to try to make it as simple as possible, is I'll limit myself to theta sub m equals pi over 2. That makes that value of sine theta sub m equal to 1, so that we get simply n times d times sine phi sub m. So, in other words, we are limiting ourselves to scanning in phi for a constant value of theta sub m. So, substituting this back into the original expression, we get e to the plus j beta times nd times sine phi sub m. Now another simplification we're going to apply here is we will let d be half a wavelength. Now, of course, d does not necessarily have to be half a wavelength for an array to work, but it will give us the result that we're looking for here. And it's important that you realize that the results we're going to generate going forward require this half wavelength spacing. We make that substitution, d equals lambda by 2 here in the expression. Beta we will write as 2 pi over lambda. Those lambdas will cancel out, and we end up with an expression that goes like this: e to the plus j 2 pi times n times 1/2 sine theta sub m. And next we're going to do a little trick, and what this trick entails is we're going to divide part of that exponent by capital N, the number of elements, and we're going to multiply the remaining factor by capital sub n. So n divided by n is 1, so we're certainly allowed to do this. And then what we're going to do is we are going to define this factor in the exponent, n divided by 2 times sine theta sub m, to be equal to m. Now this is an arbitrary choice again, so we've made a number of arbitrary choices here, but we're angling towards deriving this DFT-based multibeaming scheme. If we make the substitution indicated here, then the result now becomes e to the plus j times 2 pi times nm, the indices, divided by capital N, the number of elements. So now we're ready to show an amazing thing. If we go back to the expression for the mth beam output, that is written as the sum over the element outputs times the conjugate of the beam-forming vector coefficients. We make that substitution. We get e to the minus j 2 pi nm divided by capital N. And remember, there's a sign change here because of that conjugate symbol. So now if we do one additional thing, if we require the values of m to be spaced by 1, that is, for example, 0, 1, 2, or minus 1, 0, plus 1, or any other sequence of m's that are separated by 1, then what we get is that this is the discrete Fourier transform. In other words, this expression that we get here that gives us the output of the mth beam can be described as one element of a DFT, which is applied to the snapshot vector. Yet another way to describe this is that we are taking the snapshot vector, we are applying an n-element discrete Fourier transform, and finding that the outputs are equal to the beam outputs. Now again, this is unique to this particular set of choices that we've made about element spacings and values of m and so on. Nevertheless, this seems pretty interesting because the DFT has a lot of useful properties and we can exploit those. First, let's ask where these beams are pointing. And to do this, we'll make n equals 4, just so we can see some simpler results. If we take the expression for m, which is n over 2 times sine phi sub m, then we see that phi sub m is related to m in the following way, as an arcsine function. So we can work this out, where the beams are pointing. So for m equals 0, we see right away that phi sub m equals 0, and that's a beam pointing broadside to the ULA. For m equals plus or minus 1, we see that phi sub m is plus or minus 30 degrees, respectively. For m equals plus or minus 2, we see that phi sub m equals plus or minus 90 degrees, respectively. Now 90 degrees is end-fire, and we know that for a lambda by 2 spaced array, we get the same beam whether we point plus or minus 90. The beam we get when we point plus 90 is the same beam we get pointing minus 90, again for this particular array geometry. So the two beams, those corresponding to m equals plus or minus 2, are in fact the same beam. For any value of m greater than 2, we see here that phi sub m is going to be complex valued. Now clearly that raises a whole bunch of questions, but we're not going to address those here. We will simply conclude that the values of m that we want are minus 1, 0, plus 1, and then either minus 2 or plus 2, and we'll choose +2 just to make an arbitrary choice. So those are our 4 basis beams based on the DFT. Here is the beam-forming matrix we get. And an excellent exercise is for you to confirm that this is the matrix you get as well. But the beam-forming matrix is simply all 1s for the first column, then a combination of 1s and j's with various signs for every other element in the matrix. This first row corresponds to the pointing at -30. The second row corresponds to the pointing at 0. The third row corresponds to the pointing at +30. And the fourth row corresponds to the pointing at +90 in this particular scheme. So now we have everything we need to form beams. We can now scan a stimulus signal from -90 to +90 and then see what the output is for each one of these beams. Here are the results. In each case, we're showing phi from 0 to 90 degrees, where the center, phi equals 0, is broadside. And we're showing the normalized pattern in dB. So the maximum value is going to be 1, that is 0 dB. And I'm showing this for the 4 beams. M equals -1, M equals 0, M equals +1, and M equals +2, although you know right away this is the same beam that you'd get for M equals -2. What we see for M equals -1 is that, in fact, as predicted, the beam points to -30, but I'll also point out that we have nulls at 0, 30, and 90, which are the directions in which the 3 other beams would point. For M equals 0, that is the broadside beam, we in fact get pointing to 0 degrees as we expect, and we see nulls in the directions of the 3 other beams. And this trend continues. For M equals +1, as expected, we get +30 degrees as a pointing direction and nulls in the 3 other directions. And similarly, for M equals ±2, we get a pointing to ±90. Remember, those 2 beams are the same. And then nulls in the 3 other directions. So there's what our basis beams look like in this particular case for DFT beamforming. So why is this a big deal? And there are 2 reasons why this result is important in array signal processing theory. One is the DFT gives us a basis set of beams. We know this already from the theory of Fourier transforms and linear algebra. So as long as those m's are spaced by 1, that is, the difference between each value of m is 1, then we get this DFT for that particular geometry that we set up, and any other beam output can be computed as a linear combination of the basis beam outputs. Secondly, the DFT, which here we're writing as a DFT basis beamforming matrix times snapshot vector, that operation requires n² multiplies, as we determined earlier. But because it's the DFT, we know that the DFT can be computed much more quickly using a fast Fourier transform, and the results are the same. So this operation that we've set up, which requires n² multiplies and is the DFT of the snapshot vector, can be alternatively computed as the FFT of the snapshot vector. And the beautiful thing is that the FFT requires not n² multiplies, but only n log base 2 n multiplies, which is a smaller number. In fact, it's a smaller number by a huge amount if n is large, which it is obviously for a large array. And just to give you an example, consider an n equals 64 array, which has only 64 elements. For the 64 element array, we would find that DFT has 64 squared multiplies, which is 4096 multiplies per snapshot. For the FFT, it's 64 times log base 2 of 64, which is only 384 multiplies per snapshot. So that's less than 1/10 of the number of multiplies. That's an order of magnitude reduction in the number of multiplies per snapshot. So a huge computational advantage in doing this. There are some other aspects to this that you should know about. We're not going to go through them in detail, but I think they're useful to know about because they're discussed in the literature and in practical applications. One is the Butler matrix. A Butler matrix is what you get when, instead of choosing M to be -1, 0, +1, +2, instead you choose M to be these non-integer values, specifically -1.5, -0.5, +0.5, and +1.5. And the reason you might want to consider this is because it repositions the beams to eliminate that weird endfire beam, this goofy beam here, which isn't really a beam, it's just accounting for the two endfire directions. So if that annoys you, and in many applications it is problematic, you can instead use these choices, this choice of M, which satisfies all the requirements we talked about. Remember, M doesn't have to be an integer. M only has to have successive values separated by 1. So for this particular set of choices for M's, we get this result for the 4 beams. And now we have no endfire beam. Each one of the 4 beams points in a direction with maximum directivity in that direction, and there is no explicit pointing towards endfire. To be clear, this is still a basis set of beams, and everything else works the same. It's just a different choice for the values of M's that we use in this process. The matrix that we get for the Butler matrix is a little bit different, and just showing what that looks like. And that's really all there is to it. And of course, this is for M equals 4, but this works for any value of n, I guess, limited to even numbers. You might ask about other one-dimensional geometries. For example, we've limited this discussion to uniform linear arrays. Does this apply to a uniform circular array, for example? And the answer is it does. And there are a few minor modifications, but the principles are the same and the results are analogous. You might also ask, what about a two-dimensional array, such as a planar array? Well, again here, all of this works essentially as described here. In fact, the two-dimensional discrete Fourier transform is also expressible as an n by n matrix. The math looks exactly the same. You get an n by n matrix regardless of whether it's a one-dimensional array or a two-dimensional array. So the math itself has the same structure regardless of the geometry of the array, as long as you satisfy some basic requirements analogous to the ones that we showed for the uniform linear array. So the answer is yes, all this is pretty much the same for a two-dimensional array. In fact, you can do FFT beamforming with a two-dimensional array as well. That concludes this lecture on multi-beam concepts.